Okay, this is part 3 in a video problem set. Part 2 and 1, or previous one. In these questions in part 3, this is a continuation of kind of a long problem where we're just completing reaction equations. Okay, and these are all involving carbonyl alpha substitution problems. Let's look at first one here. At the first one, this is a mixture, what we call a hybrid reaction. Recall that the aldol involves two C double bond O's that are ketone aldehydes, the ketone aldehyde stage. Diekmann condensation, similar mechanism in all, but it also involves two carbonyl containing compounds, but they're typically both esters. What does this mean? What type of reaction is this? This reaction has an ester and a ketone. The same principles apply. What we should note here is that the ester component doesn't even have an alpha carbon. So there's no alpha hydrogen in the ester part. There are alpha hydrogens in the ketone part, two on the right side, one on the left side. This is what we call a hybrid reaction, okay? It's going to have the elements of the aldol and the Diekmann condensation. But the same principles apply. We remove a proton from the alpha position and condense it with the other partner. And this mixed reaction will work as long as one of the partners does not have any alpha hydrogens, or one of the partners is of unusual reactivity, or there's a strong thermodynamic preference for forming one product, like we saw previously with the intramolecular ones. Okay? All right, so let's look at what happens here. Obviously, we're not going to be removing the proton from the ester. I want to emphasize here that this is a common mistake I see on exams, is that people think that that hydrogen is acidic. That hydrogen is not acidic. Even though it's as close to the carbonyl group as it possibly can be, the anion, we cannot write any resonance structures where that anion is stable. It has a resonance structure that localizes the negative charge to oxygen. I.e., there's not an enolate resonance form for that anion. All right, so what we're going to do is, since it's a hybrid aldol Diekmann condensation, we're going to emphasize the fact that if it's going to be like the Diekmann, we want it to produce a stable anion that we're going to add a proton to later. All right, so what do we do here? Okay, so we're going to remove the hydrogen on the side that has two acidic protons. All right, we're going to condense it with the ester part, like before. Okay. We end up with this. Okay. An acid-base reaction is unstoppable at this point. Okay, I'm going to draw it as the anion. And we're going to add the proton back. And this is the product you would get. It's probably more stable. Actually, it's well known to be more stable as an enol. As far as an exam, I'd give you credit for either of these products, but should know that 1,3 diketones typically are more stable as enols. Okay, this is next one is a hybrid going the other way. The only acidic protons are in the ester. This is going to be a little bit harder because an ester isn't quite as acidic as a ketone, but nonetheless the same things apply. We're going to make a connection between here and here. Okay. All right, so this would be our initial product right here. I don't think we're actually going to need to acidify here. That's probably a mistake saying that we would have to do that. All right, so this is probably what we're going to get right here. Okay, there's no stable anion that can form. We can make an alkoxide. Let's see, 1, 2, 3. Now we're not going to make a cyclic ester here. Okay. All right. Okay, so this is what we make right here. How do we make this? Okay, we're going to make the anion. It's going to add and comes initially as the negative, and we're going to just protonate that with ethanol. Okay, let me say one other thing here. You may notice here that the base, NaOET, always matches whatever the group is on the ester. There's a reason for that, okay? Because the direct addition to the carbonyl is happening. It's not leading to any place, but it is a sideshow that's happening. And if that group was different than the group on the ester, you'd actually see them exchange. So they typically match because we don't want to see too many products coming from our reaction. All right, what happens here in this next one? There's two esters, but they're part of the same molecule. So this means that we're going to do an intramolecular Claisen, which actually is a totally different name reaction called the Dieckmann Condensation. Let's make this one a little bit clearer. All right, so chemists like to draw esters as COOETs for the convenience of so that their molecules don't take up that much space. But let's just go ahead and draw it out. All right, so there is our diester right there, and we know that in the Claisen condensation, Dieckmann also, we're going to take the alpha position right here and connect it to the other C double bond O group. Okay, this is going to be very favorable because if you count the number of carbons between here, you recognize that we're going to form a 5-membered ring. Okay, so again, I'm not going to go through the mechanistic details because I've done that in detail before. Okay, so we're going to have this. Okay, so sirens are going down my street. I hope that the video doesn't capture that, but anyway, so this is what we're going to get after acidification. Recognize that this molecule is symmetrical, so if I pulled the proton off of the other side and condensed it with a carbonyl, that would not have made a difference because there's a plane of symmetry in this molecule, and thus carbon that I've labeled 1 and carbon that I've labeled 4 are both technically equal to each other. All right, the next one is also a Dieckmann condensation. Okay, but remember that the Claisen condensation requires that the side that we deprotonate on has to have 2 alpha hydrogens for it to work. Okay, so if we look at this one, we're going to deprotonate one of these. meaning that our connection is going to be between that carbon and the carbonyl group. Let's again draw that out the way it looks. Recognize that here I've changed the base from sodium ethoxide to sodium methoxide to match the structure of the methyl esters here so that I don't see swapping out of methyl and ethyl groups, which is what would have happened if I had used sodium ethoxide. Okay, all right, so we're going to make the union there, or make the ring there. As you can see, we're going to form a 6-membered ring. Okay, and what do we have? All right. All right, so we have the product here. And we have the methyl group over here. Okay, so that's going to be our product. Again, I didn't go quite as much in the mechanistic details because in previous videos we had done that quite exhaustively. All right, so we're just looking at what goes where primarily in these problems here. Okay, let's look at this page. This page is an alkylation. Okay, so what happens here? Sodium ethoxide. It's going to actually do a clean deprotonation of this. Beta keto esters, pKs are about 11. Okay, so ethanol has a pK of about 16. So a very clean acid-base reaction is going to occur. And we're now going to do an SN2 reaction. This is a, say, halide at primary carbon. This is a halide at an sp2 carbon. No nitros on the benzene, so we can't do nucleophilic aromatic substitution. So the reaction is going to occur there. All right, so sorry, the anion we get is going to do an SN2 reaction like so, and our product should just simply be the product where we would take one of the original hydrogens, one of the original acidic hydrogens, and replace it with the R group. So we're taking one of these and replacing it with the whole group attached to bromine. Okay, so pull a proton off, do an SN2 reaction. This is diethyl malonate, and this is going to be the start of something called the Malonic ester synthesis. Okay, so what happens here? Remove acidic hydrogen. SN2. Remove remaining acidic hydrogen. Then another SN2. All right, so let's just look at those processes. Negative charge. Going to do an SN2. Methyl iodide is really a fantastic compound for the SN2 reaction. Okay, so step 1 got us there. Step 2 gets us here. Step 3 removes the remaining proton, remaining acidic proton. Step 4, another SN2 reaction, primary, also good. Sorry. And so this is going to give us that compound. Propyl group and a methyl group at the place where there used to be two hydrogens. Okay, this is called, in this one, this is a carbonate ester. It has no alpha hydrogens. Okay, we do have two alpha hydrogens here, two alpha hydrogens here. Carbonate ester, because of the double resonance stabilization, tends to be not very reactive as far as esters go, so we're probably going to have to use a large excess. Okay, but what's going to happen here is that, like before, we're going to remove the acidic hydrogen on this side. Okay, again, only on that side can we form the stable anion. Okay, we're going to add to the carbonyl group of diethyl carbonate. Okay. Nucleophilic acyl substitution is going to occur. Okay, again, our beta keto ester is going to be very acidic. Okay, so we're going to remove that proton. Okay. Sorry. Let me go here to actually, let's call that a methyl. Let's call that a CH3 instead of the bond line diagram. Okay. And after acidifying, we would have this. Okay, so this is kind of a hybrid Claisen-Aldol type system as well. That would ultimately, if you're only looking for the final product, that would be the final product. Again, I'm trying to keep these videos not excessively long, so I'm going to end this one right here.